Everyone, welcome to the episode 4 in distributed systems. Today we are going to talk about the distributed transactions. First, let's take a look at the why distributed transactions even exist. So for that, let's take this system. Let's say that we have e-commerce website and the user places an order. That order first should go to the order service. Order service should commit that transaction. Then after that, it goes to the payment service. Payment service should commit a transaction also in its database, and the same goes to the inventory service, and it also should commit the same transaction, and they each have their own database. How we make sure that let's say if in the payment service the transaction failed, then we also roll back in the order service. So the problem is that how to keep all system consistent if one fails mid-operation. For example, let's say that we have committed in the order service and the payment service. If the inventory service fails, then in that case we need to roll back the payment and the order service. Let's take another example. Let's say that we buy a flight. So let's say we plan a trip and we are buying a flight and the hotel, right? So but we are buying them together. So we are booking them together, because if let's say that the payment succeeds for the hotel, a payment succeeds for the flight but fails for the hotel, then in that case we are losing money, and it's a halfway booking. So in that case we need to roll back also the flight. So we need to also, if the hotel fails, then we need to also cancel the flight. So the goal is all or nothing. So if our transaction goes to the multiple system, as in this case, in case of the e-commerce or in case of the travel booking, then in that case we need to cancel whole operation. So now let's go to the challenge of the distributed atomicity. So what's that mean? So first, let's take the single database. In the single database, it's very easy, right? So we have a single transaction, single asset transaction, one log, one commit point. So we either commit or rollback. So all or nothing is guaranteed if we have a single database. But if we have a distributed system, then what happens in that case is that we have multiple databases or services. So as we have seen above, we have, let's say, order service, and we have inventory service, we have payment service, and each of them have their own databases. So that's the one issue, that we have several databases for each service. Another one is that the network may fail, right? So that the network connection may not work as we expect. And another one, that some nodes commit, other one may crash. And so we need some sort of coordination protocol for this case. So we need a protocol to ensure that everyone's commit, or if one of them don't, then in that case we are aborting that transaction. Let's take a look at the first protocol that we are using in the distributed transactions, which is the 2PC or two-phase commit protocol. So what's that mean? So in the 2PC architecture, right? So we have a coordinator and we have a participants. Coordinator, it's a transaction manager, and participants, it's a databases and services. So what happens is that in the first phase, right, it's called a prepare phase. In the first phase, what we do, coordinator asks it asks all participants that are they ready to commit? If the participants respond, if the response is yes, then in that case we are going ahead and committing that. If the one of them responds no, then and then it's the next phase, right? In the next phase, if all yes, then we are committing. If any of them responds no, then in that case we are aborting the transaction. So let's say in our e-commerce example, right? So let's say that the order service and the payment service, they respond yes, then in that case they respond yes, but let's say the inventory service responds no, then in that case we are aborting a transaction. And let's take the restaurant bill analogy. So, for example, let's say that the Alice, Bob, and Charlie, they are at the restaurant, and also we have a waiter. So in this case, waiter is a coordinator, right? And the Alice, Bob, and the Charlie, they are participants. So the first one, the prepare phase, because in this case we need to pay the full bill, right? So each participant will pay their own share. So Alice will pay their own share, Bob and the Charlie. In the prepare phase, we are asking that can everyone pay? If the Alice says yes, and Bob says yes, and the Charlie says no, then in that case the transaction is declined because we need to abort, right? Waiter aborts that because we cannot partially pay the bill. We need to all of them to pay. We need all of them to. We need all of the participants to pay. And if all of them says yes, then in that case we go ahead and they pay. And if everyone pays, then in that case we consider that as a transaction complete. So for the visual timeline, what we have, right, for the 2PC protocol, so we have a coordinator. Coordinator sent to participants either they are prepared or not. So if the first phase, we are sending a prepare message to all participants. If all participants, and we are awaiting that response from them. If all of them says yes, then we are committing. If one of them says no, then in that case we are aborting those transactions. But what are the problem? What are the problem with the 2PC protocol? The 2PC protocol. With the 2PC protocol, the problem is that if the coordinator crashes after all yes, so after we receive the all yes votes, but before they commit, then in that case participants wait indefinitely, so the resources are locked. So what it means, so for example, let's say that in this phase, right, let's say that we have received from all of the participants, we received yes, and the second phase, at this phase the coordinator crashes and coordinator cannot commit the transaction. Then in that case, what happens is that all resources are locked. So what are the real world 2PC systems, right? The first one is that for the GTA transactions, we have a Spring distributed DB ops. So also Google Spanner uses the 2PC protocol. Also RDBMS clusters such as Oracle, Postgre, logical replication, they are using the 2PC protocols. So to solve the problem that we have seen earlier, another protocol, which is that the 3-phase commit, was introduced to solve the exact problem that we have in the 2PC, right? When after the first phase, the second phase is not completed because the coordinator crashes and all systems are now in waiting state. All participants are in the waiting state. So to solve that problem, 3-phase commit was introduced. So what's the purpose of it? The purpose of it to fix the 2PC blocking problem that we have seen earlier, add pre-commit phase, and it's a non-blocking design. So what is the flow, right? So for example, in this case, we have 3 phases here. So let's say that the team manager, so let's say that we have a team manager and we have a project manager and we have a designer. So A, B, C, they are working in the same project. So the first phase for the 3PC commit is that we are sending, we have unlike the 2PC, we have 3 phases here, right? So first we are sending that the can't commit. Manager sends the can't commit. So coordinator sends can't commit and all participants respond yes. And in the second phase that the coordinator sends another request. The second phase is that the get files ready but don't upload, meaning that are you ready to commit, right? So if after that, after the second phase, the coordinator receives yes from all of the participants, then in third phase, the coordinator send request, the third request to all of the participants. Now you can upload, right? So basically, we are adding one more operation here. So instead of having committing them directly, we are asking that are you ready to commit? Then after that, we are sending do commit. We are sending a do commit. It's a third phase after which all of the participants are committing their transaction. But if the manager crashes after pre-commit, right? If the manager crashes after pre-commit, then in this case, designers can coordinate between themselves. So which means that in our case, right, in the third phase, if we, after the second phase, we are receiving yes from all of the participants, even if let's say that coordinator crashes at this stage, as we have seen that in the earlier one, right? So then in that case, coordinator can, participants can coordinate between themselves in order to commit the transaction. But let's compare them side by side, right? Let's compare that what are the advantages and disadvantages of 2PC and the 3PC commits. So is the 2PC commit is blocking? Yes, it's blocking. And about the 3PC, no, it's not. And the network is that for the 2PC it's asynchronous, for the 3PC it's synchronous. Complexity is lower. In the 3PC, obviously, we are adding one more step, it's higher. And the practical use is for the 2PC is common, so it's used, for example, most famously in the Spanner and the other databases. But for the 3PC, it's rare. The reason is that it's more theoretical than it's actual, because coordinating this part between that all coordinate between each participant, in this case each designer, right, can coordinate between themselves. It's a huge work, and the usage of the 3PC, it still remains very theoretical. So to real world insight, so 3PC avoids blocking but needs perfect network timing. So the network timing is crucial here, so that's why it's unrealistic on the internet. So the modern systems prefer other patterns, right? Modern systems we usually use, instead of 3PC, we use the consensus protocol, such as Raft, and also we are using the Saga pattern, which we are going to talk about next, and we are using the eventual consistency models. Now let's go to another pattern that is completely different from the 2PC and the 3PC, Saga pattern. In Saga pattern, we have so-called event-driven compensation approach. So what's that mean? It means that we are splitting long transaction into the small step. Then after that, each step has its own compensating action. And then what we do is we are locally commit each part, and then we ensure that the eventual consistency, and it's mainly used in the microservices architecture. So what's that mean? For example, let's take again this example of the travel booking. And in the travel booking, what we have the a book, we need to book the flight, we need to reserve the hotel, and we need to charge the payment, right? So let's say that, and these are all different services, right? These are all different microservices. So let's say that in this case, for the charge payment, right, if that is fails, so we are, unlike the 2PC and the 3PC, as soon as we receive the transaction, so each step local commit immediately, right? It means that as soon as we receive the flight, then in that case we are committing that transaction. And the reserve hotel, as soon as we receive that, we are committing that transaction. But if the charge payment, if that fails, then in that case we are sending the compensating actions, which means that we are canceling the hotel and we are canceling the flight. So that's the difference between the Saga pattern and between the 2PC. So each service commit immediately, and the system handles rollback gracefully, meaning that we are committing immediately, but we are also ensuring the eventual consistency by sending the compensating actions. So let's take a look at the Saga flow, how exactly Saga flow goes, right? The first one is that the book flight, we are committing that. The second transaction is reserve hotel, we are committing that. In the third transaction, charge payment, it fails. If it fails, then in that case we are sending the cancel hotel and the cancel flight. In case of the, for example, let's say in case of the, for example, let's go to that example again. The compensating action for the reserve hotel is that we need to cancel flight, right? For the flight, there is no compensating action, because in this case we don't have any. So this is our first transaction, but for the hotel we are canceling all the transactions that come before it. So what are the Saga implementation styles? The first one is choreography. In choreography, each service publishes an event and it triggers the next steps. It decentralized. Example of it would be that the Netflix with Kafka, but the one that we have seen earlier, it's orchestration. It's a central saga manager, directs the flow, and coordinates all the steps. It's a centralized control. So the real world examples of it would be choreographed sagas with the Kafka, AWS step functions, and orchestrated saga-like workflows. And also we have microprofile LRA, Java-based long-running actions. So let's compare now again all these three that we have with the two-phase commit, three-phase commit, and the saga. So the atomicity in this case is eventual in case of the saga, but in two-phase and three-phase it's strong. It's not blocking, unlike the two-phase commit. And for the network, it's asynchronous. For the rollback, we don't need the global abort, so we need the compensating actions. It's mainly used in the microservices, but the main usage of the two-phase commit is the distributed databases. Example of two-phase commit is banking across databases, and for the saga pattern, as we have seen earlier, it's mainly used in the microservices would be that the travel booking app or the similar applications. So the key takeaway from the saga pattern is that it's a modern approach for the microservices. So in summary, if we can take a look at all these approaches, 2PC, 3PC, and the saga. So in case of the 2PC, it's a blocking. 3PC, it's a neat synchronization. That's more theoretical than it's practical, than it has actual use. And for the saga, it's event driven at data and it has compensating actions. So what are the real world case studies? The real world case studies, as we have seen also earlier, the first one is the Google Spanner. It uses the 2PC. We have also CockroachDB. It also uses the 2PC atop of the Raft consensus. We have the Uber's microservices. It uses Saga pattern for the rides, for the ride booking, for the ride payments, and so on. So Airbnb and the Netflix, they are using the event-driven Saga architecture. So the key takeaway from this course is that, from this episode, that the 2PC, they are simple but blocking. Coordinator crashes. If the coordinator crashes, then in that case, all of the participants, they are blocked. For 3PC, it's non-blocking, but impractical. It needs perfect network timing, so it's rarely used in the real world systems. And the Saga, it's a modern preferred approach. It's the eventual consistency with the compensating actions. It's mainly used in the microservices. So again, for the microservices, we should, if one takeaway that we can take from this episode is that for the microservices, we should use the Saga pattern over that 2PC or 3PC.